Quick question, what's hotter, the sun's surface or lightning? Well, actually, it's not even close. If that seems weird to you, it's probably because you don't know what temperature actually is, but you're about to. Put simply, temperature measures how fast stuff moves, but not big stuff like cars or icebergs. Particles. If particles start moving faster, temperature goes up and vice versa. That's why lightning is so hot. It's caused by electrons jumping from the clouds to the ground, dumping insane amounts of energy, causing the air molecules to go absolutely wild. But still, 30,000 degrees is rookie numbers. Our sun's core reaches temperatures of 15 million degrees Celsius. Here, hydrogen nuclei can literally join together to make helium, releasing way too much energy. Not as much as supernovas though, which can reach about 100 billion degrees Celsius. And those still aren't the hottest. The highest temperature ever recorded was about 4 trillion degrees Celsius. At that point, solids, liquids and gases go completely out the window. The energy is so high that atoms are literally torn apart, and protons and neutrons melt into their quarks, creating a quark-gluon plasma. So, where did this happen? Right here on Earth in the Large Hadron Collider, which is a 17-mile long near-perfect circle buried 100 meters under Switzerland. It uses magnets to accelerate particles to 99.999991% of the speed of light, just to smash them together because why not? Also, you might have noticed a small issue. The particles here are already moving at basically light speed. Since nothing can go faster than light, we shouldn't be able to increase the temperature much further, but we can. That's because of this equation. To simplify, at high speeds, the energy needed to increase the temperature doesn't make the particles move faster, it makes them act heavier. Don't think about that for too long, it's weird, but it does make you wonder, what is the limit? You've probably heard of the Planck length, which is the smallest meaningful distance. It's named after this guy, but he didn't stop there. He also came up with the Planck temperature, and Planck time, charge, mass and energy. Talk about testing the limits. But anyways, the Planck temperature represents the hottest theoretically possible temperature in the universe, which is this. That number is insanely big. For reference, our entire observable universe is just 8.8 times 10 to the 26 meters wide. That means to measure 1.4 times 10 to the 32 meters, you would need to line up 160,000 observable universes. Also, I would tell you what happens above this, but we don't really know. Our physics literally just doesn't work. So now that we've hit the upper limit, what about the lower limit? Negative 273.15 degrees Celsius. That's it. We literally cannot go any colder because at this temperature, the particles are not moving, so they can't go any slower. That being said, it's also impossible to reach this because particles don't really like standing still. By the way, you should subscribe or I'll show you what high temperature actually looks like.